So I had a lot of fun prepping this chapter. Like I feel like this is a potentially very meaty chapter of the book, and there's a lot that you could dig into. I'm glad that I had to prep this one because there was a lot of it that I could have skimmed over without like realizing there was an ocean beneath me. And so, yeah, the book glosses over some things or sort of mentions some things in passing that I think are like, ooh, there's a lot here, and some other things it goes into more detail on, and then says later, this actually isn't terribly important for data scientists. So, because we have a limited amount of time here, I kind of picked certain things to focus on here. I'm not going to try to like give an exhaustive outline of what the book covered and just mention it because you have the book and you can read it, and that's the whole point of the book club. But I'm going to kind of dig into what seemed to me to be the central idea of the chapter, which didn't always come out if you skimmed it kind of quickly. But with that introduction, here's what I identified as some of the learning objectives for this chapter. It's mainly about populations and sampling and what we do with that. And then the last half of the chapter seems to be like a list of distributions, and we will probably go through that part pretty quickly. Here we go. So yeah, the order that I'm going to take this in is kind of roughly following the book, but it won't line up exactly with the book's table of contents because I wanted to digest this and then present it in a way that made sense to me, and hopefully that'll help it make sense to you too. So the chapter, as I said, is about populations. Now, almost everything in this chapter seems to have a particular meaning in statistics. And I know that I've used these words in a sense that is not the technical statistical sense, but for this chapter, I'm going to try to stick to what I understand to be the correct statistical usage. So a population, I'll put it in my own words, so I might be wrong still, but a population, as far as I understand it, is like a set of things that we care about. Now, this could be a concrete set of things, like represented by actual people, but more generally, it's an abstract idea. And I give some examples here. Like a concrete population that we might care about is the people who will actually vote in the next election. And I'd like to understand that population for certain purposes. Another population that we might care about is, let's say I have a breeding pair of fruit flies, and there's a whole set of possible offspring they could have. That set of possibilities is another population. Now, there will never be all the actual individuals possible from that population because it's a huge abstract set of possibilities, but that's a population. A useful population that I'm going to kind of work with as the mental model I have is like a huge forest of trees, and all those trees in the forest are the population we care about. So that's kind of concrete, but you can also generalize this to more abstraction, like a forest of trees. So we represent these populations for statistics as distributions. And this is how we deal with the populations. They're distributions over one or more variables. So if we're talking about a voting population, it's a distribution over the candidates that are up for election or the propositions or whatever. If it's the population of trees, this could be a distribution over a million different variables. Trees have a height, they have a diameter, they have a thickness of the bark, they have a species, right? There's a million possible variables that the population of trees is a distribution over, and so on and so forth. You know, the population of dice outcomes is just a distribution over the number rolled. So if I roll a pair of standard 6 dice, then that population represents this distribution between 2 and 12. Now, I said a population is something that we care about, and it's generally that we care about something that we could calculate for that population. And that thing we could calculate is called a statistic. Which this is a case where my usual usage of the word statistic doesn't cover the statistics use of the word statistic, because really a statistic is any function I could calculate from a distribution. it could be something that we're all familiar with, like the mean. The mean of a distribution is a statistic. The mode, the median, just all this stuff we talked about last time, measures of central tendency or just, or spread, those are statistics, but a statistic could be anything. And I give like a crazy example. Maybe I want to know for this forest, what's the median height of all the trees divided by the MAD of the number of branches? Like that's a statistic. I'm pretty sure that it's a statistic that's not useful to know, and it'd be crazy and badly behaved if you tried to calculate it. But a statistic is something we want to know about the population that we calculate from the distribution. Okay, before we go on, because like this is something that I spend a while internalizing. I want to make sure that we're all on the same page with this. Are we familiar with what I mean by a distribution? We talked a little about this last week. We'll work with the usage of population and statistic. So the statistic that we want to know for the population is the population statistic. Now, we pretty much never actually have access to the population, like full access. And that's what the whole field of statistics is about. How do we learn something about the population? We don't have access to it. And the answer is, well, you take a sample from the population. So now the word sample here has a technical sense in statistics. It's some number of individuals, and I'll just kind of use that word broadly here, that are drawn from the population. So if our population is people who will vote in the election, then the sample of individuals is some set of likely voters. Or for the trees in the forest, the sample would be a random subset of those trees. If I want to sample the population of dice outcomes, I'd roll the dice a number of times, or breed the fruit flies, or whatever. So that's a sample. It's some number of individuals, and we're going to use N here. I think this is pretty common usage to represent the size of that sample. There's other sizes we'll talk about. N means the size of the sample. It's some number of individuals that are drawn from the population. They're drawn at random. At least that's in principle, you draw them at random. And this is a well-defined process because you're representing a population as a distribution. So we can draw randomly from a distribution, and that's how we sample. And then the sample that we get is another distribution. It's the distribution is the sample, and it's a distribution of the same variables as the population, at least the variables that we care about. So instead of calculating the statistic that we wanted to calculate for the population, the best thing we can do is calculate that statistic for the sample. And I'm going to a couple times switch over to this demo. The book in one of the additional readings has this URL. Oh, have a hand raised there.
Yeah.
Yes.
Hi. Can we see the previous slide, please?
Okay. Yeah.
All right. So this last statement, whatever statistics we wanted to calculate for the population, we instead calculate for the sample, right?
Yep.
So when we have a population and we want to do modeling, do we care to do modeling on the population, or we care to do the modeling on sample? I'm looking about the size of the data while doing modeling. Will it be useful to do modeling on the population rather than the sample if we are not doing some kind of exploratory statistics, but modeling tags?
So this is kind of the important point here, is we can't generally do modeling on the population because all we have is the sample. The population, you can think of as this abstract idea. I mean, even if it's concrete, like all the trees in the forest, which in principle, we could make a sample that is the population for that case.
Okay, so maybe let me put the question in another way. So for example, if we have large amount of data, can we use modeling on that even if it is like 3 gig data?
Oh, the sample could be huge. Yeah.
Okay.
I mean, it's limited by resources and time.
Oh yeah, I get it. Okay. Even the sample is so huge, no matter how huge it can be.
It's just the sample.
Oh, get you.
If I roll the dice like 1 trillion times, it's still just a sampling.
Yeah.
Of that space possibilities.
Okay. Okay. Thank you.
So yeah, so this is that bit of terminology that I've in the past been kind of lazy and clumsy about. But for this purpose, the population, almost by definition, we don't have direct access to. All we can work with is the sample.
Well, it depends on what you define your population to be.
True. Like, I mean, you could define a population like that is completely accessible, but it's useful, I think, to think of a population as something that I only access via a sample. Like I could define the population that I care about to be like these 2 sets of pencils. Like this is my population, I have it. But most of statistics, the point of statistics is that we don't have that. If we do have the whole population, then we almost don't need to like everything we say is authoritative about that population.
Yeah. Also, in the book, the section where he talks about size versus quality, when does size matter? I think he also made mention that maybe for kind of exploratory analysis, if, for example, we have large amount of data, we can do some kind of exploratory with subsamples of the data to understand the data rather than to go and do, I think, modeling on the whole amount of data. What can you say about that?
So I think that some of this will become clear in the next few slides, because a lot of what this chapter is about is like getting your mind around when is the sample good enough? So ask me this again if it's not clear in a few slides. Or if at least, maybe I'll make it more confusing, but either way, like if we're not aiming in that direction, then let's bring this up again, because in some ways that's kind of the whole point. Okay, so I was saying that there's this useful link in the book that I'm going to switch over to that I found really helpful for visualizing and understanding what this is. So this is a simulation that starts with a population. So here they call it the parent population. This population, you can select a few different distributions for it. And then you get to draw a sample. So I'm drawing a sample from the population, and I calculated a statistic on it. In this case, the statistic was the mean, right? I can draw a different N. I can draw a 25, N25 sample from this population. Now here, in this case, for this simple demo, we do have access to the population because we defined it, right? So this is an example of, I know what the population is because I've defined it in a way that I have it. But if we pretend that we don't have direct access to it, right? You can't see it, but I'm covering the top half of the screen, right? And I draw a sample, and then I calculate a statistic. Let's see, I can calculate all kinds of things. I can calculate the MAD. I want to know the MAD for the population. I can't, I have to draw a sample. And I calculate the MAD on the sample. One more metric that I was going to say, I could calculate the range. This is a particularly dangerous metric to calculate. And calculate the range of the population. So I draw a sample, and I calculate the range from my sample. You can see generally the range of my sample is going to be less than the range of the population. Okay, so population and sampling. Now you can probably see already that there's a problem that we have. It's unavoidable, is that this sample is not the population. Almost always, right? In the cases, in all but the trivial cases, the sample is not the population. So that means that the statistics that we calculate on the sample are not going to be the same as the true population statistics. If I sample a population of something and calculate the mean, that mean will not be in general exactly equal to the mean of the population. There's several reasons that this sample is different from the population. The most obvious is random fluctuation, right? I drew a random subset, a random sample from the population, because the fluctuations, like that's, the statistics calculated on that will generally not be the same, just because of the random differences. The book goes into bias a bit. There's different kinds of bias. Bias is different from random fluctuations in that it tends to a certain direction. There's selection bias, which is due to my sample not being random enough. Right? There's some systematic difference between my sample distribution and the population distribution. And the book talks about different ways that selection bias could happen. Regression to the mean is a phenomenon that happens because there's a selection bias in what you're sampling. If I'm sampling the extreme members of a population, then the conclusions I draw will generally not hold for the whole population because I have a selection bias there. And regression to the mean is one manifestation of this kind of selection bias. The book kind of mentions, I mean, it hardly mentions it, and it glosses over sample size bias. But I think this is important to kind of understand. This is a bias for particular metrics, not because our sample is, we have a selection bias. We have a completely random sample, but just because our sample is smaller than the population, there's a bias. For example, if we're calculating, if the metric we care about is the range, and I draw a sample for the population, the range of my sample is always going to be less than or equal to the range of the population. That's by the nature of what range means. And so some statistics that we calculate will be systematically off for the sample as compared to the population. And so those particular metrics have a bias. Some metrics are known to be biased. Some metrics are known to be unbiased. I couldn't find a terminology for this besides just the word bias. So I will refer to that as sample size bias, because it's something that generally, the smaller as your sample size gets larger, if you have a biased sample, if you have a biased metric. Okay, so this is the problem that most of statistics, I think, is not too much an exaggeration to say, most statistics is trying to get around this problem, get a handle on this problem, that the sample is not the population. Ideally, so what I'm saying right here is sort of like, in an ideal world, if we had unlimited time and resources and access to things, here's how we would get around this problem. We would just take lots of samples. So I want to know how close my sample comes to the population. If I take one sample, I don't know, is this close? Well, what if we did it again? Would it be different? I don't know, let's do it again. And we do it again and again and again. We do it 1,000,000 times. So in principle, we do this a large enough number of times that it doesn't matter if we do it again. I'm not going to use a symbol to represent the size because it's going to be like huge. So ideally we'd sample a large number of times. And then what we do is for each sample, we calculate the statistics that we care about. And so we get 1,000,000 of those. And then we have a distribution over those statistics. Okay, so you got to keep in mind here, we have like 3 different distributions we're talking about now. We have the population, which is an abstract distribution you can't directly access. We have the sample, which is itself a distribution. And then we have lots of samples and then a distribution over the statistics calculated for those samples. This makes a lot more sense in the demo here. Okay, so here's our population. Let's say I care about 2 statistics for this. I want to know the mean and I want to know the MAD. And let me say that for both of them, I'll draw samples of size 25. Now the way this does it is it will draw a separate sample for each one. Okay, so I'm drawing a sample from the population. I'm calculating the mean of that sample. And then I'm drawing another sample of 25 and calculating the MAD for that sample. In practice, I've calculated mean and the MAD in the same sample probably, but the demo, it's doing 2 separate polls. Okay. Are those good estimates? Now, if I don't see the parent population, you can't see, but I'm covering my screen, right? If I don't see the parent, how close is the mean there to the population mean? How close is the MAD to the population MAD? I don't know. Hey, but let's see. All right, let me do the same experiment 10,000 times. And I have a button here, I push it, and it'll do the experiment 10,000 times. Boom. There it is. So the distribution of those bottom 2 plots, that's the distribution of the mean and the MAD that I get if I repeat this experiment 10,000 times. And now I have a sense of, okay, where is, if I do this experiment, where is the mean likely to fall? Well, I take the mean of the distribution of the means, and that's 8.07. So I say, it looks like that's, here you can see that's pretty close to the mean of the population. But what I really am trying to get at is, like, what's the spread of this here? If I did another sample, because usually in reality, I only have to do 1 sample. And I make that sample as big as I can, right? Because the sample kind of is defined as everything I gather. So I do my sample, and I want to know how close it is. Well, if I could do this experiment and do my sample 10,000 times, I'd say, well, the standard deviation of the distribution of the means is 1.26. So I clear this again and I do 1 animated sample. If I magically knew that 1.26 standard deviation, and I get the result that from one sample, okay, it's doing the second one too. But from my 1 sample, it takes the value of 9 or something. Well, that should be within about 1.26, give or take. That's a standard error here. We'll get to what that means. That's within 1 or 2 units of the true mean. But I don't know that. Like, how do I, without actually doing my experiment 10,000 times, how do I know what the standard deviation of this distribution of samples is? And the same for the MAD here. If I want to know the MAD of my parent population, if I could do 10,000 samples, I get a distribution for the sample statistic. But if I don't have the resources to do 10,000 runs, how do I know this? Okay, do you all kind of see the problem here? Because it's like a real problem, and it's the problem that statistics is trying to get at. So what I'm describing is, in an ideal world, sort of this is conceptually what we want to do, is we want to do our experiment 1,000,000 times. We want to draw 1,000,000 samples and see what the distribution of sample statistics is. Okay, and as I was saying in the demo, the distribution of those sample statistics, which is called the sampling distribution, that helps us understand the results of our sample experiment. The mean of that distribution is an estimate of the thing that our experiment is aiming at, which because we might be calculating a biased statistic, that the mean of the sampling distribution might not be the mean of the parent population. And the standard deviation of the distribution would be an estimate of how much random fluctuations are influencing our measurement. Since the book glosses over bias a bit, I do want to say a little bit more about this kind of bias. Let's suppose that one of the, here, I'm going to draw like a custom distribution like this. This is the population that we care about, right? And let's suppose that I want to know the range of this population. Ranges are particularly, as I said, delicate statistic to calculate because all it depends on is like the bottom end and the top end of your population. If I draw a single sample, I might get, in this case, I think I got the full range. I think the range of my sample in this case is equal to the range of the parent population because I got lucky. You see that? Because I happen to get an individual from the lower end and the upper end. But let me do samples 100,000 times and you see what happens. And because I kind of picked this compact population and sampled it a lot, most of my samples have the full range of the population, but some don't because I got unlucky and I missed an edge. But you'll see here the mean of this distribution is always going to be less than the true range of the population. So for this particular metric, for this particular statistic, the range, it makes sense to, instead of taking the mean, to take the max, right? The max of my sample range is a better estimate of the range of the parent population. The mean would be a biased estimate because it's systematically low. So range is an easy case to see, but some of these others, like median, is also a biased estimated statistic. I think probably MAD is too. Some statistics are biased, some aren't. I'm not enough of an expert to tell you right off which aren't. But this is known that some are biased and some aren't. Okay, so the process we've just described is like conceptually what we want to do to understand the limitations of sampling. As a bit of an aside, the central limit theorem, which the book talks about, and then says it's not that important for you guys, but the book talks about it a bit. It's in the special case where the statistic that we care about is the mean, it can be shown that the sampling distribution of the mean approaches a normal distribution. And this is really important, the standard deviation of that distribution, that is the distribution that we would get if we did 1 million samples, the standard deviation of that distribution is given by the standard deviation of one sample divided by the square root of the sample size. And I think this is easier if we actually, here, I'm going to draw another weird old custom distribution, not at all normal, right? And I want to calculate the mean for n equals 20 samples and mean for n equals 5 samples. So when I say n equals 5, I mean the size of the sample is 20 versus the size of the sample is 5. And let me take 100,000.
You didn't choose mean.
Oh, thank you. Yes, it won't do anything if I don't choose mean. Okay, I'm going to do 100,000 samples here. And what you see is the resulting sampling distributions of the mean look pretty normal, even though my parent population is not at all normal. You can do a little fit normal here, fit normal here. I can, keep sampling millions of times. That's the central limit theorem. If my sample statistic is the mean, in that special case, the sampling distribution will be what we call a normal distribution. It's a Gaussian. And the standard deviation of that distribution is the standard deviation, or estimated by a standard deviation of an individual sample divided by the square root of the sample size. Now, I don't have right here, I could do an animation, right? I don't have here an individual sample, but I will in a minute. It doesn't have a calculation of standard deviation for me. But you can see that if my sample size goes up by a factor of 4, so I go from the n equals 5 sample size in the bottom up to the n equals 20 sample size in the top, the standard deviation went from 4.05 to 2.02. It went down by a factor of the square root of the sample size. So this is where the rule of thumb comes from, that you're probably familiar with in statistics. If I want to reduce my error bars in half, I have to have 4 times the amount of sampling data, 4 times the size of the sample. And that's a consequence of this right here. But I want to emphasize, this is a special case. This is the case when the statistic I care about is the mean. The central limit theorem does not apply for other sampling statistics. If I switch this to, let's see, variance and MAD, those look pretty normal actually. But in general, like they won't be. I can come up with like median, and we already saw range right here. Like those are definitely not normal. So the central limit theorem is specifically about mean statistics. But when I said those are not normal here, I didn't mean like those are strange and unusual, right? I meant like those are not normal distributions. Okay, yeah.
So based on like reading how you're supposed to calculate like standard error of the mean, what you would do is draw, if you could, like draw a bunch of samples and then calculate the mean for each of the samples, and then from that do this. And so I have a question, because in my field in neuroscience, it is really, really common on graphs to show the standard error of the mean, even though you have only like done one group of mice. You've ran one group of mice and you have the mean of their speed or something running through a maze. And I'm wondering if like then it's incorrect to use the standard error of the mean in that case, because you've only done one sample.
And
like an N of like 6. So you bootstrapping on it seems also weird, because it's like the central limit theorem does presume some number, right? Some like larger distribution.
If your sample size is really, really small, right, then like almost all bets are off, right? There's some assumption here that your sample is to some extent representative of the population. Yeah, but what you're saying is like that's exactly like the difference between, this took me a while to get my head around this like nuance. Like when there's the square root of n here, and this is because of the central limit theorem and the special case of the mean. If I have just one sample, I'd like to know the standard deviation of that sampling distribution. I don't have it, but I can estimate it by taking the standard deviation of my sample and dividing by the square root of the sample size. Now, if the sample size is really small, like, I'm sure each field has rules of thumb for what's big enough to take seriously. Like some statistics you can't even calculate if your sample size isn't like a certain minimum size.
Thanks. Oh, statistics.
Yeah. So now we're getting to kind of what I've been describing is like a problem that we have only a hypothetical solution to. But now we're getting towards something that's actually practical. So yeah, if our sample statistic is the mean, as we were just saying, we can estimate the standard error from a single sample. And there are some other, if we want to do the theoretical legwork, then we can also do that for some other sample statistics. Like, there are theoretical bases maybe for estimating the standard error of other statistics besides the mean from a single sample. But in general, if I want to calculate some arbitrary statistic for my population, and all I have is a single sample, so far it seems like I can't do it. I have to repeat that sample many times to get that sampling distribution. Now, if I actually did this, I wouldn't care about the standard error for my original sample because I have like a super sample, which is 1,000,000 times bigger. And now I want to know what the standard error on that super sample is. Right? So like it's really a hypothetical solution to do my sampling over and over again. In practice, though, the bootstrap is a really great way around this. So let's talk about the bootstrap a bit. It might feel a little magical when you first hear it. And I say it's a simple but powerful technique for estimating the standard error of any sample statistic from a single sample. You can also, given some mild assumptions, obtain an estimate of the sample size bias for your statistic from a single sample, which, wow, we didn't even get that from doing 1,000,000 samples. Like, am I trying to sell you something? So here's how it works. First, we start with the assumption that our sample distribution is not too far off of the population distribution. Now, like this, I have to mention this assumption because really everything is built on this assumption. If their sample is not representative of the population, then nothing we can do. Like we can't magically infer something when we have like a completely non-representative sample. But if the sample distribution is representative enough of the population distribution, then here's what you do. We're going to construct a new simulated population by assuming that our sample is completely representative. And we do that in practice just by taking our sample and multiplying it a gazillion times. In practice, this just means when you draw from it, you replace what you drew because you never run out. Now you just do a lot of simulated experiments on your simulated population. I now have this simulated population, and I can do cheaply 1 million experiments by drawing 1 million samples. So I draw 1 million samples, let's call them bootstrap samples, from my simulated population, and each sample is the same size as my original because I'm trying to understand how sample size n behaves. Now I can calculate my sample statistic on the bootstraps. So now I have the distribution. It's a bootstrap distribution. It's not, it's not the real sampling distribution that I'd get if I did 1 million experiments, but it's as close as I can get with one sample. So I can calculate the standard error of that distribution of bootstrap sample statistics. I can calculate some other things too, like confidence intervals. We'll talk about in a little bit. I can even get an estimate of the bias because I can see how that distribution of my bootstrap samples, how the mean of that varies from the mean of my simulated population. And we can use the same demo here to get a feel for how this works. So I'm going to try to do something in sort of a two-step process. So let's say I start with, I'm just going to turn this off. Right now, I don't care what statistic I'm calculating. I'm going to start with my parent population, and I get to draw one sample. I'm going to draw the biggest one that the simulation allows, which is 25. Okay, now I'm going to do, you see that distribution there, my sample? I'm going to try to replicate that above. So I take that sample. Okay, I can't see it anymore, but it's something like this. Doesn't matter if I get it exactly right. Right? It was whatever, right? Something. You get the idea. This is my one sample that I'm now promoting to be a parent population. You get that? All right, now I'm doing bootstrapping. I'm going to draw from that sample. The sample that I drew doesn't look like the original sample because I'm resampling it, right? With replacement. Okay, let's suppose I care about the mean and the median. And so I'll do 100,000 bootstraps on my simulated parent.
Do you want to change n on the median?
May as well, yeah. Let's make them both, 25 because that's what my original sample was. Okay. All right, so I get this bootstrapped sampling distribution, which tells me the standard deviation is 1.27, right? So that's the standard error of my original estimate of the mean. So the mean of the parent, the simulated parent, which is my original sample, is 9.4. So if I'm reporting the mean of the original population, I report it as 9.4 with a standard error of 1.27. And that's a bootstrap standard error. Let's see. It was a sample, the standard deviation of my original sample was 6.36, and a sample size of 25. Square root of 25 is 5. If I take 6.36 and divide it by 5, I don't have that math right there. That's not too far off of 1.27. Okay, so like the central limit theorem is working, right? If I calculated the median, let's see, here's my bootstrapped distribution for the median, the mean of that is 7.7. Now note that's not the actual median of my sample here, of my simulated parent. Now something I've noticed, and I'm not an expert in statistics to know whether this is anything, but it makes sense to me. Remember how I was saying if our sample statistic is the range, like the mean is a dumb estimate for that. You want to take the max of your like your sampling distribution for the range, because that's what range, that's the nature of range. Every time I've run this, the median of the distribution of medians matches the median of the parent really well. And it makes intuitive sense that it makes more sense to take the median of the medians than the mean of the medians. But I'm probably going off into like statistical heresy here, so I'm not going to like lead you down. But the mean of the medians is a biased estimate. Like, and you can't like always do this. Like I could have a statistic that I'm calculating that I can't like take the statistic of that statistic all the time. And that won't always make sense. Like the range of the range wasn't the right thing to do. It was the max of the range. So this is not like a general rule of thumb. I'm just pointing out that the mean of the sampling statistic is not always like the right thing to do. But you can test this by bootstrapping. You have your simulated parent, your simulated samples, and you can see how your statistic behaves. And that's really the power of bootstrapping here, right? It's not magic. Bootstrapping won't give you like a better estimate of the sampling statistic. I mean, knowing the bias can help you be careful, but it's not like it fills in gaps for your data. It doesn't fix any selection bias that you had in the original sample. Like all it's doing is it's helping you understand the limitations of your original experimental procedure by simulating 1 million of those experimental procedures on a simulated population. So apparently the bootstrap has an interesting history, which I'm only vaguely familiar with in terms of books and publications and discussions. It feels at the beginning a little bit like snake oil, because I'm promising you like a really easy solution to a really thorny problem. So it's important to kind of understand what the bootstrap can do for you and what it can't do for you. Like you're simulating your experiment on the best simulation that you can. And that helps you understand the limitations of your experiment, but it doesn't give you a better experiment, if that makes sense. Okay, the book at this point talks about confidence intervals. And I think that the idea of a confidence interval is pretty intuitive. It's the interval, let's say a 95% confidence interval, is the interval that would contain the central 95% of the values for the sampling metric, the sampling statistic, if you did the sampling experiment a large number of times. And again, you can't usually actually do samples a large number of times, so to estimate a confidence interval, you bootstrap. And then your 95% confidence interval would be the interval that contains 95% of the bootstrap sampling statistics values. A standard error, which is defined as the standard deviation in that sampling distribution. Standard error is like a particular confidence interval. It's a confidence interval. You do plus or minus 1 standard error, and that's about a 68% confidence interval. So reporting standard error, reporting confidence interval, basically the same idea. It's giving you a sense of that, the spread of that sampling distribution. Okay, the next half of the chapter, I'm going to kind of breeze through. It goes into this catalog of distributions. And it might strike you as a little bit like odd to do this. And a lot of these distributions, they say, this is useful in this test, or this is useful in that test. And then in future chapters, we'll actually cover those tests. So I think that for now, I'm just going to kind of breeze through them and say, this is what the distribution looks like, and then kind of move on. Because when we get to future chapters, we'll actually understand if the distribution is really important, we'll understand why, because we'll be using it in the right context. Okay. But for each of these distributions, R has a built-in, I think for all of these cases, built-in implementations. So you can sample this distribution and you can plot the histogram. So for each one of these, I sampled the distribution 10,000 times and give you a histogram and also a QQ plot, which the book, every time I come across a QQ plot, I have to remind myself what this actually means. It's a measure of normality. That is how close your sample is to a normal, how close the distribution is to a normal distribution. And the QQ is I'm plotting the quantiles of each data point as they would be in a theoretical normal distribution versus my actual distribution. And every time I get it to make sense to me in my head, I have to think about it again because it's a little, anyway, I have to think about it twice, but maybe you guys can get it right away. So like if my points get further away from this line, so that means down over here and up over here, that means my sample quantiles are, a point is bigger in a sample quantile than it is in the normal quantile, which means I have fatter tails. Yeah, see, it's hard. Anyway, so I'm going to breeze through some of these distributions and we'll see how normal they are and move on. The normal distribution is a pretty important one for theoretical reasons. And the book kind of downplays it. It says, the normal distribution has been overplayed. But as you'll see, almost every other distribution has a limit in which it becomes very normal. So like the normal distribution is kind of a big deal. Students' t distribution came up for mostly obsolete reasons now. And it's normal, but depending on which particular distribution, because this is actually a family of distributions parameterized by degrees of freedom, it'll be more or less normal. So there's a limit in which this distribution is normal. There's a binomial distribution, which is more of a discrete distribution. It's like flipping a coin. And if I flip, let's say 6 coins at a time and make a distribution of the number of heads I get, you get something like this, which is kind of an approximation to normal. The book talks about the chi-square distribution, which again is a family of distributions that's parameterized by this degrees of freedom. And for different values of degrees of freedom, this can look really normal. I picked one for which you can see it's pretty not normal. Why is this important? I think we'll get to it later in the book. The F distribution is another one that's I had never remembered. I will forget again after this hour until we get to it in the book where they say the F distribution is useful for this test. But again, it's parameterized by 2 degrees of freedom. And there's a limit in which it's normal, but you can see it's also skewed. Poisson distribution is one that comes up in physics a lot. And it's parameterized by lambda. This is a discrete distribution like the binomial. And in the right limit, it becomes pretty normal. And okay, I think the book had a few other distributions related to the Poisson. I didn't go ahead and put those in because I figured we were already getting tired of looking at normal-ish distributions. But it's kind of nice to have the names flashed in front of you because then when you see them later on in context, like, oh yeah, that's a distribution that looks something like this. Okay, 6 minutes to spare. Now, I've been seeing that chat's been coming up, but I can't see it on my view right here. So are there any questions I need to go back and deal with, John?
There was a lot of discussion in the chat. I don't know if there's anything that we need to go back to, but if I'm wrong, if anyone wants to bring something up out of the chat, let me know. I think we kind of had our own little resolutions over there.
Okay.
Yeah, that was great. Like this chapter is like who said it? Pavitra said that this chapter is everything. It's like, okay, let's cover all the things.
Kind of felt like that.
It's very cool. I know for sure that the chi-square and F distribution do get talked about later because they weren't covered in the first edition of the book in this section. They were only covered later. And I looked at that and it looks like you get basically the same material. They just went a little bit more in depth into the actual distribution in this part. Let's see what's coming in. Oh, and yes, Scott has a link for skill versus luck in sports, which is interesting.
So sampling selection of regression to the mean cases. Yeah.
Another important thing that came up in chat is next Monday is a holiday in the US. It's Memorial Day, and so we will skip next week and just meet the following Monday for chapter 3. And we need someone to present chapter 3. So if anyone is available for that, that would be great. I will bug people in the Slack if we don't have a volunteer right away. It is good. Yes. So chapter 3, I think, is a bit of a long one. So it's probably good that we have 2 weeks to get through it. Well, I mean, I don't know. They're all pretty long, but it's about 50 pages. What is it about? This is the, oh yes, experimentation and significance testing. So I think like so far it feels like every chapter we're going to go, oh, this is like everything. I think splitting it in half probably isn't a bad idea. So does anyone want to take the first half of chapter 3? Anyone? Looking at, okay. Well, we'll talk about it on Slack when someone can do it. So does Morgan do you want to take the second half of chapter 3, Morgan? All right. So Morgan's got the second half. So in 2 weeks, someone will be doing the first half, and if it has to be me, it will be me. But
where's the split between first and second half?
I don't know yet. Let's see. I feel like there's probably a fairly good split. I mean, about 25 pages or 24 pages in, something like that. We'll figure it out for sure. Exactly where. I think probably after p-values. I don't want to combine, over 100 pages and do too much all at once. I think let's take it slow and see. But yeah, okay. We'll talk in the Slack about who's going to do it, but you've got 2 weeks to figure it out. Let's try to read, I think through the end of the p-value section, but I haven't had a chance to really dive into the chapter to make sure that's a good splitting point. Cool. Anyone have anything else they want to talk about? Want to ask?
I want to suggest that if you don't follow any of the other additional resources in this chapter, you follow the link to this simulator, because it's fun to play with and it gives you a good sense of what's going on.
I'm curious, what is onlinestatbook.com? Did you go to the root?
Let's see.
That's funny. I am OpenStats. Developed by Rice.
Right. They're really into the OER.
Yeah. So we probably should just keep that handy for the rest of the book. It probably has some other resources that we'll want to play with. So cool to know. All right. I will see everybody on Slack.